Hello. Today we're going to be covering energy levels in atoms. We're going to start with a bit of background before we go on to describe line spectra, and then we're going to talk about where those line spectra come from, including transitions in atoms. Finally, we're going to perform some calculations to calculate the emitted and absorbed photons inside atoms. As you may know, all warm objects will emit electromagnetic radiation. That is, everything that's above 0 Kelvin will emit some radiation. Objects at room temperature, for example, will primarily emit infrared radiation. You may be very used to seeing this when you see images from infrared cameras. The sun, on the other hand, will emit a very broad spectrum of electromagnetic radiation. This will include some infrared, but also will include a lot of emitted visible light and ultraviolet radiation. The spectrum for sunlight is shown. A spectrum is any graph that shows the intensity of light against the wavelength. Here's another graph showing the observed spectrum of sunlight. In yellow, we have the measured spectrum of sunlight at the top of the atmosphere. However, in red what we have is the measured spectrum of the sunlight when we observe it at sea level. As you can see, there's a clear difference between these two graphs. Certain bands or wavelengths of light are missing when we measure the spectrum at sea level. The reason for this is because there are gases in the atmosphere which absorb certain wavelengths of light. This red spectra is an example of what's known as an absorption spectrum. A related effect happens when we look at the light that comes from a specific gas. If we look at the spectrum of light given off by hydrogen, for example, we can see that only specific wavelengths are being emitted. This is what's known as an emission spectrum. All of these effects can be explained by the transitions of electrons between energy levels inside atoms. For example, absorption occurs when an incident photon is absorbed by an electron inside an atom. This moves the electron from a less excited state to a more excited state. By contrast, light is emitted from atoms when an electron moves from a more excited state to a less excited state. This coincides with the release of a photon. In order for us to fully appreciate this, we need to have an understanding of energy levels inside atoms. Inside atoms, electrons are only allowed to exist in certain shells corresponding to their energy level. It's forbidden, for example, for an electron to occupy any space between these shells. That is, electrons are only allowed to have a certain amount of energy inside an atom. For simplicity, energy levels are usually drawn like the diagram on the left. The labelling N corresponds to increasing energy level, where N equals 1 is referred to as the ground state. This is the lowest energy level that an electron can occupy inside an atom. As electrons move down energy levels, they will emit photons. These photons will have an energy corresponding to the difference in the energy levels of the electrons. Electrons can only exist in an excited state for a finite amount of time. Eventually, they must always fall back towards the ground state. As discussed, absorption corresponds to an increase in the energy level of an electron inside an atom. Only certain photons are going to be absorbed, however, which correspond to the differences between the energy levels inside the atom. Here's a chance for you to have a go at some questions. Pause the video and write down some answers for the following questions. My answers will follow shortly. And here are the answers. Next up, we'll have a go at calculating the energy of these emitted photons. By convention, the energy levels inside an atom are usually specified as being negative. Shown in the diagram is an atom with 4 different energy levels, n equals 1, 2, 3 and 4. However, that corresponds to 6 separate possible transitions and hence 6 separate photons which are emitted. The energy of an emitted photon hf is equal to the difference in the energy levels of the electrons as it transitions from one state to the next. For example, let's look at the first transition between n equals 2 and n equals 1. The difference between these energy levels is equivalent to 10.2 electron volts. Therefore, the emitted photon will also have an energy 10.2 electron volts. It will very often be important that we convert this energy from electron volts into joules. So it will be equivalent to 1.63 times 10 to the minus 18 joules. Often, we'll want to calculate what the frequency of the emitted photon is. If we think back, the energy of a photon is equal to hf, and so the frequency is E over h. Putting our numbers in, we can see that the frequency of the photon is going to be 2.46 times 10 to the 15 hertz. Finally, it's frequently going to be very important that we can also work out what the wavelength of the photon is. Thinking back, the speed of light is equal to the frequency multiplied by the wavelength. So rearranging our equation and putting our numbers in, we get that the wavelength is equal to 1.2 times 10 to the minus 7 meters. And lastly for today, here's an opportunity for you to have a go at a question yourselves. Calculate the wavelength of the 5 other possible transitions in this atom. Pause the video, write down your answers, and my answers will shortly follow. And here are the answers for transitions 2 to 6.